Now in this slide we can see different images that are being generated by thermal imaging camera, and it senses the radiation that comes out of the body. So we can see that there are different pictures, a picture of a lady, some guys coming out of a gallery, a dog, a hand, and automobile vehicles at road. We can see that how the thermal imaging camera senses and generates these images. It takes the radiation coming out of the body, and it puts that radiation in a perspective, and do the math, and let us see these pictures. We can measure temperatures using these non-contact type sensing techniques. We can see that the engines are heated because of its temperature. They are then the front portion of car is bright yellow, and there's less amount of thermal energy in the cabin, so it is like purple or black. So we can see the human hand is also generating certain radiation. Humans are generating, animals are so every material, either engineering or non-engineering, it generates the heat, it generates the radiation. Sometimes it falls in human visible capability to view the color. Sometimes it's not, but the material generating the radiation, this is emissivity. So emissivity is the capability of the temperature of a body to emit the radiation at certain temperature. Higher the emissivity, higher the radiation heat transfer. Lower the emissivity, lower the heat transfer because of radiation. Now the formulas for heat transfer because of conduction, convection, and radiation are presented over this slide, and you can see, and we will discuss the what is K. K is the conductive heat transfer coefficient. Higher the conductivity of material, higher the value of K. A is the cross-sectional area from which the heat flux passes. D and T, dt or dx is the temperature gradient. What is the temperature difference of two bodies, and what is the distance between them? In the convection, H is the convection heat transfer coefficient. It depends upon a lot many things, and you will calculate heat transfer coefficient because of you will discuss, you will learn convection heat transfer coefficient in detail in another course, that is heat and mass transfer. Then is A, what is the area where molecules are being forced unnaturally hitting the surface and taking the energy from it and moving on. In convection, we know that a medium moves in the heat convection. So what is the area? For example, the a particular example we considered in convection was the block of hot copper placed in a beaker filled with water, and water molecules are taking heat. So the walls of block, hot copper block, is the area from where the molecules are taking the energy. So A is that area. T is T infinity. What is T infinity? T is infinity that if we have uh, this copper block wall, and obviously it is at 4, it was on 400 degrees centigrade, uh, as we discussed. Now molecules near to it will have more thermal energy than the molecules relatively away from the wall, than the molecules from far away, than the molecules far away. So there will be temperature difference between this molecule layer, and this molecule layer. There will be temperature difference, spatial temperature difference, depending upon the space coordinates. So if we keep moving away from the body, then we will come at a point then that there will be no further temperature difference between these layers of molecules in a water medium, as we have considered in this example. So what is the temperature, or have we take as T infinity? Okay. For example, if you take a copper block and put it at 400 degrees centigrade and put it in a room on a table, and initially the temperature of room was 25 degrees centigrade. So now if we keep moving toward the copper block, we will observe that the air will keep getting hotter until the temperature of the molecules that is colliding uh, the surface is 400 degrees centigrade, nearly 400 degrees centigrade. The more we move toward the block, it will be getting hotter, and if we move away from the block, then we will come at a point where if we move further away, there will be no temperature difference, and this temperature is known as T infinity. T surface is definitely the temperature of copper block. Then there is radiation heat transfer, and we can say that there is emissivity epsilon, and there's the Stephen Boltzmann constant, there's exposure area, as we have discussed in previous slide, and T4. What is T4? For instance, um, T4 is low temperature, the body of low temperature. Body at low temperature is T infinity in this case, and T surface is the body at high temperature. And we can see that we take the power of 4 and then we take the difference. These are formulas we use for heat transfer. And you have noticed that there's a dot over Q. Q is heat conduction, there's a dot over it here. Q dot. What is Q dot? Q dot is rate of heat transfer. By using these formulas, we can predict, we can calculate and estimate the rate at which heat is being transferred from higher temperature and lower temperature. Not exactly the value of heat. It will be the watt joules per second, calories per time. So these are formulas to calculate the rate of heat transfer, not the amount of heat that is being transferred. We can integrate it over the time, and we can calculate the amount of heat that was transferred. But these formulas estimate the rate of heat transfer, not the heat transfer. So, since we are talking about the energies in the form of heat, it's a good time that we talk about the internal energy, specific heat because at constant volume, and specific heat at constant pressure. So, what is internal energy? Internal energy is the energy possessed by mass atom due to motion of its atoms. Its rotational motion, because of its vibrational motion, whatever motion molecules possess, and they constitute toward the development of energy. It is internal energy, and we can quantify this internal energy per unit mass, and we can say that it is specific internal energy of mass, as we have been talking about the specific volumes and other specific quantities that relates to thermodynamic characteristics. Therefore, the same aspect the same principle is being used, and we can find the internal energies from our thermodynamic tables. You can take time, you can read this text on the slide and develop further understanding for a while. Now we can see that we have a constant piston cylinder assembly on this slide, and it represents that there are certain amount of mass in the form of volume, in the form of liquid, and in the form of vapors as well. So what we if we want to find the internal energy of this specific system, we will what we will do that we will find the internal energy of liquid and internal energy of the vapors, and we use the formula that uses the value of x is the quality, and quality defines the ratio of mass present in the form of vapors divided by the total mass. So and you can see it in this equation over here. So we have been using these formulas in the form of to find the volumes, and we will use the same formula to find the internal energy in this case. What we will do, we will go to our thermodynamic tables, and we will look into the temperature, pressures, and volume, and we will find the internal energy at of the liquid part, that will be given in the form of UF, and that of the vapor form in the form of UG, and we will use these quantities in this formula, and we find the total internal energy of our system, as we have been doing in the case of finding the total volume. We have been previously using V is equal to Vf plus X Vfg formula, and just what we have done is we substitute V with U, and you see it's the same formula. We will use this formula to find the total internal energy of this pure substance. When we talk about pure substance, we know that we have thermodynamic tables given for different pure substances, and pure substances when we have the single material considered as our system. When we have mixed materials, we will have to go into further mathematics, and that we will be discussing in later part of this course, and that is thermodynamics 2. Presently we are only consider that whatever system we are talking about, it contains a pure substance, and it might be present in the form of liquid or vapor, but it should be the same material, and it should be the homogeneous material as well. So now let us consider this table, and try to find a pattern over here, where we can see that the internal energy is given for a variety of temperatures and over variety of pressures. We have superheated steam over here, and we can see that the internal energy of a steam at different pressures and different temperatures is represented in this table. Now observe that if we move along the pressures, for instance, if we have steam at 200 degrees centigrade and at different pressures, 10, 100 and 500. Yes, you will see that there is negligible difference if we move along the pressure at the constant temperature. We increase the pressure, but the internal energy is not increasing as much as if we increase the pressure. For instance, we have 700. So if we increase pressure from 10 kilopascal to 100 kilopascal, the internal energy of these different steams at 200 degrees centigrade only increases by only differs by few kilojoules per kg. However, if we move along the temperature and we increase the temperature at a fixed pressure, for instance, we move our system and we increase its temperature from 200 to 700 degrees centigrade while maintaining 10 kilopascal as our system pressure, we can see that there is a much increase in the internal energy. So the difference between these two values is much greater if we take difference of values internal energy when we move along the pressure. So what we observe that internal energy strongly depend upon the temperature, and it negligibly changes when we move along the pressure. We changes the pressure at a constant temperature. So it is a much better function of temperature than the pressure. So we can conclude that the internal energy is much sensitive to the temperature, and it remains nearly invariant of pressure. Now we consider a system and in which we have a constant piston cylinder assembly. If we confine this piston and we restrict its motion, then we will be converting our system into a rigid body system in which there is no motion of boundaries, and thus there will be no work that we can do on the system or system can do on the surrounding. Now if we write first law of thermodynamics or the work energy principle for this system, you will see that so this work is going to be 0. So if if we use any sort of mean to heat this process, heat the system up, or to cool the system down, it will only be increasing or decreasing our internal energies. So this is what happens when we restrict the boundaries and make a rigid body system. It will influence more whatever heat we are giving to the system or taking out of the system. It directly influences the internal energy of the system. So we can also say that the specific heat of a pure substance at a constant volume is really in the reality is difference of internal energies as different states. Now enthalpy, what is enthalpy? Here our textbook presents a system in which there is a constant pressure cylinder assembly, and he wanna develop understanding of enthalpy, and while discussing this constant pressure cylinder assembly, but it confuses some students when they then when they move on, and the system is not a constant pressure, and then they confuse about the concept of enthalpy over there. So enthalpy is nothing but it's just it's an artificial characteristic or a property of thermodynamic property of a system, based on the based on a concept that if internal energy is a property of a system, if pressure is a thermodynamic property of the system, volume is the thermodynamic property of a system. So here we have three of them: pressure, volume, and internal energy. So if all these three characteristics are well established thermodynamic properties, then their combination must be a thermodynamic property of a system. If we multiply pressure into volume and add internal energy into it, uh, it must be equal, it must results and into a characteristic that must also be the property of system, because all three of these are in properties. So their combination must be the property of system. So if we don't know about anything about enthalpy, we still can can study thermodynamics, but for and we are 100% capable to quantify or qualify different aspects of thermodynamics. But what we are doing over here, we are making our job easy, and we are introducing another thermodynamic property that will help us to further uh, calculate different uh, uh, different will help us to solve different problems using less amount of mathematics. This is what we have done in the when we introduced polytropic processes, and we have already discussed that we don't know anything about polytropic processes. We are still able to find the work and different quantities. But what we did previously that we introduced polytropic process, and we eased up our calculations. Now we are doing the same thing. We are introducing another thermodynamic properties. If we don't know anything about enthalpy, we are still able to study thermodynamics. But if we introduce the enthalpy, it will be relatively easy. And how it is easy, you will be seeing it in the coming slides. And the same formulas that are applicable to volume to find the internal energy are still applicable to find the enthalpy of a system. So enthalpy is nothing but the combination of different thermodynamic properties, and in this slide we can see that if we for instance we say that we have saturated water vapors at 0.6113 kilopascal. So where is 0.6113? So what should be the volume of this system? Since we said that we have saturated water vapors, so volume of system must be 206.132 meter cube per kg. And what should be the internal energy? Since we are talking about saturated water vapor, so UG 2 375.33 kilojoules per kg must be specific internal energy of the system. Now if we use the definition of H, and H is equal to U plus PV. So U is equal to 2375.33 plus 0.6113 into 206.132, and what it will generate, it will be exactly equal to 2501.35. You calculate it, it will come exactly 2501.35. So enthalpy of a saturated water vapors at 0.6113 kilopascal, if is equal to product of pressure into volume plus this quantity. If you take the product of these two quantities and add up with this, so this will be the same if we have mixed phase. We will use the information of quality. We will find the volume, respective volume. We will multiply the pressure, and then we will use the information of quality again. We will and find the internal energy. We will take the product of volume into pressure plus internal energy. It will be equal to the enthalpy of the system. So enthalpy is nothing but the combination of different thermodynamic properties. Now we have specific heats to discuss, and as I have indicated in the previous slide, that the internal energy of a rigid body, if we heat it up, our system, or we cool it down, we will be directly changing our internal energies at the two stages. So, it is also presented over here in this slide, that change in internal energy over temperature is the constant specific heat. Previously we know that Q plus W is equal to delta U. So since for a rigid body, work is equal to 0, so Q is equal to delta U. So if we change if we give heat to our system, and we wanna know that what is the change, so it will be the change in internal energy, and since we already know that Q is equal to mCp delta T is equal to delta U, so sorry, Cv, constant volume, so Cv is equal to delta U over m delta T. So for a specific system in which we talk about the energies of a unit mass, so we can ignore this, and we can say that Cv is equal to delta U or delta T for a discrete system. and for a continuous system dv is equal to du over dt, and this is what we are talking about. Now if we talk about a system in which we don't restrict the volume. So if we don't restrict the volume, now if we have a system in which we do not restrict the motion of boundaries, we give it certain heat, specific heat, and we look into the dynamics of system. So we will know that there may be some motion of this piston up or down, depending upon we are giving it heat or taking the heat away. So because of its motion, its free motion, now if we talk about the work energy principle, we have both work and the and change in internal energy. So since delta U is equal to 1Z2 plus PV, because work is combination of is the product of pressures, change in pressures and change in volumes, and we if we take the convention of the text of this textbook, this sign will be minus, because this book considers that if we work on the system, it will be negative. Then delta U plus PV is equal to Q1C2. If it is a constant pressure assembly, then the value then throughout the transition of system, the pressure remains constant. As you can see in this system, picture of this system, it is a constant pressure cylinder assembly, and we are talking about the specific heat at constant pressures. So the system is valid for our case, and we can see that now if we give heat to the system, it changes enthalpy of the system. Why enthalpy? Because this combination is enthalpy. We already know that H is equal to U plus PV. So since we have transition of system, delta as for a constant pressure, so 2 plus P, pressure is constant, volume 1 so 2. So we can see that now if we talk about the specific heat at a constant pressure, it will be change in enthalpy. It will change in enthalpy, but there must not be the change in the phase of system, that there must be no transition of this substance from liquid to solid or liquid to vapors, or any other phase transition. For a single MCP, delta T is equal to delta H in this case, and Cp is equal to delta H over m delta T. For a specific case, for a unit mass, it is delta H over delta T. So specific heat is change in enthalpy over change in temperature, whereas it was change in internal energy over change in temperature for the case of specific heat at a constant volume. So This is valid for solids and liquids. However, in the case of gases, we know that for ideal gases, we can use ideal gas law, and for a unit mass, it takes the form of PV is equal to mRT. Here m is equal to 1 for a unit mass, so PV is equal to RT. We already know that enthalpy is equal to internal energy plus PV. So we can replace PV by RT over here. And since we have already seen in previous slides that where we discussed a table and we concluded that the internal energy is more sensitive to temperature and negligibly sensitive to pressure. So internal energy is a function of temperature. We can conclude that internal energy is only the function of temperature, and it negligibly changes and nearly remain invariant to the change in pressure. So if u is a function of temperature and r is constant, T is again temperature, so this whole equation that represent H is equal to U plus RT is a function of temperature only. U is a temperature, is a function of temperature, and RT, there's R is constant, T is temperature. So the combination of these two terms is only function of temperature. And now we already know that if we derivate it with respect to temperature, so what will be getting partial h over partial t. So if we have only one variable, independent variable, we can use dh over dt instead of partial h over partial t is equal to du over dt plus r t over dt. And if we simplify this, we will get this. Since this term is change in internal energy over a change in temperature is equal to Cv. We already know that. In the previous slide we have derived it, is equal to plus R is equal to Cp. So Cp minus Cv is equal to R. This is what we were trying to achieve. So if we talk about gas constant of any specific gas at certain temperatures, uh, we will come to note that it is the difference of that pure substance and difference of what quantities, difference of specific heats at constant pressure and constant volume. Now we have to see that or this we can see on this by this graph that the specific heats of the pure substances or pure gases, pure substances, that's more appropriate. It is a function of temperature. We previously, you must consider that specific heats remain constant for whatever cases, but it's not true. Specific heats change when we change the temperature. Why? Because it is more easier to heat the 1 kg of water from 50 degrees centigrade to 51 degrees centigrade, but it is relatively difficult to heat the same amount of water from 2000 degrees centigrade to 2001 degrees centigrade, because that's the prime definition of specific heats. It is the heat required to raise the temperature of a pure substance by 1 degree centigrade. You can see that we are talking about water, and if we wanna talk about this temperature, this is the specific heat, and if we talk about 2000 degrees centigrade, then this is specific. We will be needing more heat to raise the temperature of water from 2000 degrees centigrade to 2001 degrees centigrade, as compared with uh, raise in temperature by 1 degree centigrade at 250 degrees centigrade or something like that. So if temperature increases, specific heats increase. So it is not constant, and we must know that what temperature we are talking about, what ranges of temperature we are talking about. We can say that it nearly remains constant for a short range. For instance, it will remain constant. We can say that over here it will remain constant. In this span it remains constant, nearly remains constant. But it changes substantially. Specific heats change substantially when temperature varies substantially. So we must keep it in mind.